Okay, so a few things from the previous slide set I need to mention so you can go over them. There were a bunch of example problems I want you to do. The answers are listed on the PowerPoint. If you actually download and play the PowerPoint, you'll see them. But a few other groups you need to learn the names for. So sometimes you're unable to get every double bond in the main chain, right? So we haven't seen an example like that yet, but you can imagine a really long chain. In fact, it's branched into two parts. So one's maybe 10 carbons long or something, and then somewhere off the middle is a 4 or 5 carbon chain or something like that. And every one of those ends has a double bond in it. Well, there's no way to get all the double bonds in the main chain. So there may be one somewhere sticking off the chain, right? It's entirely possible. So these are the names of these double bonds as substituents, right? So it could only be 1 carbon long at the top here. It's a methylene group. Sounds like methyl, but we added the ene ending to indicate it's a double bond, right? Fairly easy. So if you can imagine a really long chain, maybe it's 50 carbons long or something, and it's got a couple double bonds in it, or 5 or 6 or 20 or whatever it might have, and then somewhere off of that chain is sticking a double bond, right? It's a substituent, like a methyl group, but it's double bonded. There's no way to get it in the main chain along with all the others. So you have to name it as a substituent. So it'd be called a methylene. Right, the next one, if it's 1 carbon longer than that, so the side group here is only 2 carbons long, the main chain would be attached right here, right? So if it's 2 carbons long, you'd think it'd be called an ethylene, but it's not. It's called a vinyl group, right? It's got a specific name, and we're going to add that to a vocabulary list. Remember, I'm treating this like you're learning a foreign language, so we need to learn some vocabulary. So a 1 carbon double bonded substituent, methylene. 2 carbon double bonded substituent, where the double bonds at the end here, is called a vinyl. And if it were 1 carbon longer, 3 carbons long, is called an allyl. Someone's microphone's open. So you have So you have a methylene, a vinyl, and an allyl group. So 1, 2, or 3 carbons with a double bond at the end. And some examples on the right. Right? And the other part I left out from last time that we didn't get to was the difference between the different types of isomers. Okay, so we have to go over these just vocabulary words and definitions. And so what's an isomer? An isomer simply means that 2 molecules have the exact same parts, right? Isomer, same parts. So they have the same formulas. But if you look at how they're put together, they're connected differently. That's all it means. So to have an isomer, you got to have the same parts, the same overall formula, but something's connected differently. Okay? Those are called constitutional isomers. Their constituents are put together differently. Right? They're parts. If the carbons are the thing that's put together differently, then we call them skeletal isomers, because the carbons represent the skeleton. If the carbons are all put together the same, but some other atom, like hydrogen or oxygen or nitrogen or anything other than carbon, is put together differently, then we call them positional isomers. So either the skeleton or the non-skeleton, we call it positional, are put together differently. Right? Let's look at some examples at the bottom. So I've got 7 examples here for you, and I can pick any 2 here and have you compare them. So let's compare the first 2, right? The one 1-hexene and the one that's labeled 3-hexene. Okay? So these 2, do they have the same parts? Do they have the same formula? Well, let's count carbons. They each have 6 carbons. Do they have the same number of hydrogens? I'm not going to count them. I'm going to ask, since they have the same number of carbons, if they have the same number of sites of unsaturation, then the hydrogens will match, because they're applying the same rule. So they both have 1 double bond. So they have the same number of hydrogens, however many that may be, and if you wanted to calculate it, you'll find out that it's 12. But however many it is, I don't have to do the math, I know they're the same. Right? So these have the same formula, so therefore they are isomers of each other, because they're not identical. What's different? Are the carbons connected differently? No, all 6 carbons are still in the same line. Right? There's no branching here, like there is in these over here, so they're not skeletal isomers. What's connected differently then? The hydrogens. right? So in the end here, there are 3 hydrogens, right? And this end only has 2. So clearly a hydrogen has been removed from this carbon and placed somewhere else to make this one, right? So the hydrogens are connected differently. And another way to see that is the double bonds in a different position, right? That's why it got its name. So these are positional isomers, right? How about the 3-hexene and the one below it, right? The one labeled 3-hexene and the one directly below it. Do they have the same formula, right? So this one has 6 carbons. This one has 6 carbons, right? So 1, 2, 3, 4, 5, 6. And they both have 1 double bond. So the number of hydrogens will also match. Of course, the number of oxygens also matches 0. The number of plutoniums also matches 0. Every element matches, right? So they are the same formula. They are isomers of each other because they're not identical. Are the carbons connected differently? Yes. This is 6 in a row. This is 5 in a row with 1 off of it, right? That's not necessarily the longest chain for the name, as you can tell. We did this one last time. But they're connected differently than this one is. The carbons are connected differently. So this is a pair of skeletal isomers, right? As would be this pair, skeletal isomers, or this pair, right? But these 3, any pairing of the first 3 here would be positional isomers because all the carbons are connected the same, right? You guys do this one with me.
I have a question.
Go ahead.
Could you explain how you named the 2-ethyl-1 butene? I'm just confused, like why it wasn't named with a 3.
Because when I get the butene name, it's these 4, right? And I start numbering from the end that gives a double bond the lowest number, which is this end, not this end. This end would give the double bond a 3. This end gives a double bond 1, so it's definitely a lower number, 1. That puts the ethyl group on 2.
Okay, thank you.
Okay, so let's try this pair here. All right, so this pairing, are these isomers at all? And if so, are they skeletal or positional? Well, the first thing we do, we count carbons. This one has 6. This one has 6. Do they have the same number of hydrogens? I do so by counting sites of unsaturation. This one has 1 double bond, no triple bonds, no rings. 1 double bond, no triple bonds, no rings. Yes, they match. So again, they each have the same number of hydrogens. You don't have to calculate how many, as long as you know you arrive at the same answer. Are they connected differently by their carbons? No, the carbon backbone is exactly the same, right? Now, this may have been drawn, say, down here instead of over there. That's the same thing. Keep that in mind, right? So these are drawn correctly. As far as their carbons are concerned, they're the same, so they're not skeletal isomers. The hydrogens, again, are in different positions because of the movement of that double bond. So these are positional isomers, okay? So 2 of these names are actually incorrect, and I'll leave it up to you to find out which 2. You're practicing your naming, so go back and look through these, and the answer is going to show up in just a second. But pause the video if you want to try it, and look at which ones are missing something. So 2 of these are actually missing a feature that you need to add, and if you're finished trying it, keep playing the video, and you'll see that these 2 need a trans nomenclature, right? Because they do cross the double bond, right? And the double bond is cis or trans possible. All these others, like this one up here, this one down here, and this one here, and this one up here, cannot be cis nor trans because the 2 things on this side of the double bond are the same. They're both hydrogen. Okay. Right, and lastly, for this slide set, I want to go over the different isomers for longer things like 4 or 5 carbons and so forth. So here's all the 4-carbon alkene isomers. We did this on the very first day where we talked about hydrocarbons. There's only 2 ways to put 4 carbons in a chain, either 4 in a row or 3 in a row branching, right? But if you have a double bond, we have another possibility. I can put 4 in a row, 4 in a row, or 3 in a row and branch it, but the 4 in a row has 2 options. I can put the double bond on the end or in the middle. So I want to do every possible option. These are all the isomers I can do, and they each need unique names. Right? With the 5s, we said there were 3 possibilities of alkenes, right? The pentane, the isopentane, and the neopentane. If you want to name these more rigorously, it would be a methylbutane here, right? And this would be a dimethylpropane. But if you throw in a double bond to the mix, now instead of 3 possibilities, there are 5. And there's no mathematical way to predict this. You just have to do them, right? And the double bond could be put on this 5-carbon chain in 2 places, right? It can be put on this chain in 3 places, that's the other 3 options, and it cannot be put on this one at all. You cannot put a double bond here because it would result in 5 bonds to carbon. So these 5 are a result of placing double bonds on these 2 options. Okay? And once again, 3 of these names are incorrect. And I want you to go through and figure them out. So if you're watching this again, pause it and try to figure out which ones they are. Maybe a cis or trans is needed. Perhaps I've included a number that is unnecessary and so forth. So, right, so that's the case here. Right? These 2 things here need cis and trans possibilities because there exists differences on each side. In fact, both of these are trans. And this one down here, the 2 is unnecessary. Right? So 2-methylpropene, where else would the methyl group be? It's 1, 2, 3. The methyl cannot be anywhere but there, so the 2 is unnecessary. So these 2 are trans, and that one doesn't need the number. Right? And the last thing about these cis and trans options in these alkenes, which we'll talk about more as soon as we start the next PowerPoint, about their reactions, is they have slightly different properties. So here we have a cis-2-butene versus a trans-2-butene, right? And they differ in their boiling points by very, very small amounts, right? It's just a 3-degree difference in their boiling points. And their densities are also slightly different, right? The cis-2-butene is slightly more dense, very slightly more dense than the trans. And the reason for that is the same for both of those. This one has a higher boiling point. Remember, boiling point is a measure of how much energy or heat you must put into something to rip one away from the crowd, right? And this one takes a little more effort to do that than this one does. And what's the reason? Well, if I take a bunch of cis-2-butenes in a solution, right, in a container as a liquid, put them together, they're stacking each other like a bunch of stacked cups. See all this little cup shape here? Whereas with the trans, they can't do that, right? They can just sit side by side, right? They can bind to one another, but not quite as well as the stacked cups here. So this one has a slightly higher boiling point resulting from the slightly tighter packing, which is why it has a higher density. So it's not much difference, but there is a difference. Okay? Over here, I have a 1-butene, right? So it's 1, 2, 3, 4 carbons where I drew out these hydrogens. And cis-trans is not possible here because this end of the double bond, there are not differences, right? And this end, there are differences, but I have to say yes to both ends in order for cis-trans to be possible. Over here, this one had differences. There's a methyl and a hydrogen. On this side, I had a hydrogen and a methyl, right? So each side had differences independent of each other. Here, there's no difference on the left, so it can't be cis-trans. Here, there's no difference on the left or the right, so it can't be cis-trans. Okay, so look at this name at the bottom. 2,4-heptadiene, right? So how long is it? Hepta means 7 carbons. It has a double bond. There's the ene ending. In fact, there are 2 double bonds. That's why the di is stuck right there. I would not put the di in front of the hep because there aren't 2 7-carbon things. They're in fact 1 7-carbon thing with 2 double bonds. I put the adjective in front of the thing it's describing. So it's a 7-carbon chain with 2 double bonds in it, and these are their positions, 2 and 4. So if you draw these out, there's 4 possibilities because I didn't tell you how those double bonds were arranged. And in fact, every one of these, the double bonds have a different arrangement, either both trans, both cis, trans followed by cis, or cis followed by trans, respectively for 2 and 4. So when you see a name like this, go ahead and draw it out, but I didn't tell you how to draw this, so the possibilities for each double bond that can be cis or trans, it doubles the number of options. Okay, so if I gave you a long chain with 3 double bonds in it, and the double bonds are not on the ends, and each one could have been cis-trans, there are 8 total possibilities, because 2 times 2 times 2 is 8. Okay? And then the rest of these slides in this slide set talk about how this is the basis of a lot of biological features, and I'll do one example and leave the rest for you to look at, is when we have our visible light hit our retinas, right? There's a molecule in the back called retinal, right? It's an aldehyde, which we'll talk about later, but it's got this series of double bonds in it, which you don't have to memorize, but every one of them here, right, is in the trans conformation. They're all trans. All of these are in the trans conformation, those that can be, right, all 4 of them. When light hits this molecule, it flips this one to its cis conformation, right? So this molecule is now cis at this position, right? So the first double bond is trans, the second one is trans, this one cannot be, it's an aldehyde. So first, second, third, fourth, first is trans, second is trans, third is trans, fourth is trans. when light hits this, right, or in fact it starts out cis and turns to trans, but when light interacts with this, the second double bond changes from cis to trans, or you leave it alone, it goes back to cis for after a while. And this tells you how you can see light. So this molecule changes from cis to trans, right? The protein holding it must change conformation. It's called rhodopsin in the back of your retina. And when the protein changes conformation, these little tails on the outside send an electrical signal down a nerve, and your brain gets the information that you saw a photon of light. Now, if you stare at the sun, which is a very bad idea, don't do that, then all of these will get converted from cis to trans, and it takes time for them to revert back, which can cause permanent damage if they're all turned to trans and damage the protein. Okay, there's some more examples after this that you can look at, but let's move on to our next slide set so we can finish up the reactions for these hydrocarbons. Okay, so let's look at some reactions for the ones we've talked about. The first reaction we've already mentioned once, and I gave you an idea of what the products were last time, is called combustion. Right? Combustion is just another name for burning. Right? So I'm going to take some hydrocarbon, all carbon and hydrogen, add molecular oxygen, right? And the two products, if it's pure hydrocarbon and just oxygen, the products will always be the same. It's carbon dioxide and water. If I were to start with ethane, I just draw the structure of ethane here. It's just a line, right? Two carbons. I add molecular oxygen, O2, right? And I get CO2 and water out of it. But you're going to need to balance the equation. I think you did this in your previous chemistry course. But you need to balance the carbons, hydrogen, and oxygens. So the first thing you want to balance is the thing that appears in the fewest places, right? And that's going to be your carbons, because the carbons only appear on one molecule on the left and in one molecule on the right. So let's balance those. So there are 2 carbons in ethane. There's 1 carbon in CO2, so I would write a 2 in front of the CO2. This was 1, this is now 2. Right? A 2 is a coefficient. The next thing to balance is the other element that only appears in once on each side. That would be the hydrogens. So there are a total of 6 hydrogens here, right? And this one ethane molecule. And I need 6 on this side, so there are 2 hydrogens here, so I'd write a 3 in front of this water. So far I have 1s over here, and a 2 and a 3. And finally, let's balance oxygen, since it appears in the most number of molecules, right? There are 2 oxygens in carbon dioxide. There was a 2 in front of it, right, from our previous assignment, so that's a total of 4 oxygens. There's 1 oxygen in water. There's a 3 in front of it, right? That's a total of 3 more, so 4 plus 3 is 7. So over here I have 2 oxygens. In order to get to 7, I need 3.5 of those things. So I'd write 3 halves, or 3.5. Sorry, 7 halves, or 3.5 right here. And then when we're done, it would read 1, 3.5, 2, and 3. And that would be the answer for 1 ethane, right? And that might be the question on your test. How many oxygens does it take per ethane? It would be 3.5. So what we like to do is not have any fractions in here, so we multiply by the lowest, by the denominator of each of the fractions. In this case it was 3.5, so we multiply everything times 2, and we get 2, 7, 4, and 6 is the answer. But on your test, I will ask you, how many oxygens does it take per ethane? Then you may as well just leave this a 1, because you're going to have to divide 7 by 2 to get the answer. Okay? For ethene, you may notice it takes fewer oxygens, right? Same number of carbons here, but fewer oxygens, because this one is 3.5 per ethane, this one's only 3 per ethane, right? And if you went to ethine with a triple bond, still makes the same product, CO2 and water. Here it takes 2.5 per ethane, because we have fewer hydrogens, right? So I need fewer oxygens to make all the water. Okay, so combustion, we always result with CO2 and water, and you're going to have to balance these things. So do quite a few examples. Here's 3 of them here you can walk through, and there's many on the practice tests. Okay. The other reaction we're going to do is addition. Right, so here we're taking a molecule like ethene, right, our favorite little double bond, and we're going to add H2. Right? Not O2 this time. We're not burning it. This is just addition. So these two things are going to be added together. I'm not going to lose any atoms. I'm going to put them all together and make the final product ethane. You see the double bond is becoming a single bond, right? And these H's are adding 1 to each carbon. So a red one over here and a green one over here. Right? So this addition is called symmetrical because I'm adding a symmetrical molecule, H2, to a symmetrical double bond. Each carbon on each side of this ethane looks identical to the other one, right? This one's got 2 H's on it and it's double bonded to a carbon. This one's got 2 H's and it's double bonded to the other carbon. So each side is identical, it's symmetrical, as is the H2. The H's are identical to each other. So in this case, which H goes on which side is sort of irrelevant, right? It doesn't make any difference. You end up with the same thing. That's what symmetrical means. Right? To get this reaction going, because if you take ethane and H2 and put them in a jar together, nothing's going to happen. I need to get it started, much like combustion. I need to get it started. So I increase the pressure or the heat, add a metal catalyst to get it going, and then it'll do this reaction. Right? So it turns the ethene's double bond into a single bond, and I've added the H2. This is called hydrogenation because I'm adding hydrogen. I'm not adding water. Adding water would not be called hydrogenation. It would be called hydration. Like when you hydrate, you're adding water. But if you were to add H2, you're adding hydrogen, right? That's the real problem with the name of the first element. It's got a very poor name in hydrogen, and that it was named for the ability to originally generate water when you burned it. Right? So H2 and O2 make water. So it's got a very poor name, but it's stuck. It's not changing. Right? So we're going to still call it hydrogen. But the addition of H2 is called hydrogenation, whereas the addition of water, which we'll see momentarily, is called hydration. Okay? What if you're adding something else, not hydrogen? Let's add bromine instead. So this is called bromination because I'm adding Br2. If I were adding 2 chlorines, you could probably guess it would be chlorination. If I were adding 2 iodines, it would be iodination, right? So I just make the name whatever it is, right? But in more general, if this just said XX, remember X is our general representative for a halogen, right? So bromine, chlorine, iodine, and so forth, are fluorines. If I'm adding those, I call it halogenation. So this is a generic term, right? Halogenation means I'm adding either Br2 or F2 or I2 or Cl2. They're all halogens, so it would be called halogenation. This one more specifically is called bromination. So you can be very specific in this answer, but if bromination is not an answer choice, it's still halogenation. Okay? Again, it's symmetric. Each side looks the same. Each side looks the same. One bromine goes on each carbon. Very simple. Okay? It can be asymmetrical. So I'm starting with my ethene again. This part still looks symmetrical, but I'm adding an asymmetrical molecule, right? So this is HCl, right, or hydrochloric acid. So this molecule isn't the same on each side. But it really doesn't matter in this case because this side is still symmetrical. One side's going to get the H, one side's going to get the chlorine. Which one goes where is sort of irrelevant because it's the same on either side. Right? This is still an asymmetrical addition, but we don't have any issues because we end up with the same one whether you draw the chlorine here or draw the chlorine there. This is termed hydrohalogenation, right, for the hydrogen and the halogen. You more specifically can call it hydrochlorination because I'm using specifically chlorine here. If I'd been using HI, right, it would be hydrohalogenation still, but a more specific answer would be hydroiodination. Right, so you can name it very specifically. At the bottom is another example, ethene, symmetrical again, and I'm adding water. Right? Water is an asymmetrical molecule. One side's going to get the H, one side's going to get the OH. Right? Which carbon gets which is sort of irrelevant because this one's still symmetrical. But this is termed hydration because I'm adding water. Right? In this case, again, I'm going to have to add some sort of catalyst to get it started, and I use sulfuric acid. Okay? But the really important ones are the alkene also being asymmetrical, right? So here's propene, right? 1, 2, 3 carbons with a double bond, right? So these 2 carbons are now not the same. They're not symmetrical to each other. This carbon on the left is double bonded to the other carbon with 2 H's, and the one on the right is double bonded with a H and a methyl. So these are not symmetrical. And when I add a H2 to it, for example, each side would get H, and that doesn't make any difference. But if I'm adding an asymmetrical molecule to another asymmetrical double bond, then I have a problem. I could put the H on the right and the chlorine on the left and arrive at this answer. Or I could put the H on the left and the chlorine on the right and arrive at a different molecule. These are not the same thing at all. Right? If I turn these around, it's not the same anymore. So which one will it do? Right? So will it put the chlorine on the left or the right? Right? So how do we know? So Vladimir Markovnikov came up with this in the 1870s, and he said it a little differently. Of course, it was in Russian, but he said you're going to put the hydrogen, this is the English interpretation of it, you're going to put the hydrogen on the carbon that has the most hydrogens already. It's the easiest way to think about it. Okay? And then the chlorine, the non-hydrogen thing, is go on the other carbon. Right? So a very short way of remembering it is the rich get richer, and rich in terms of hydrogen. So of these two carbons, which has the most bonded hydrogens already? The one on the left has 2, and one on the right only has 1. These hydrogens up here are not on this carbon. They're on this carbon up here. So I'm asking about this carbon in particular, the 2 that are in the double bond. If the one on the left has 2 H's, the one on the right only has 1, so who has the more hydrogens? The one on the left. So the one on the left is going to get the hydrogen. So that means this is the answer, right? The one on the left gets the H, not the one on the right. Okay, so, and the chlorine, of course, the non-hydrogen part of this molecule, goes on the other carbon, whichever one doesn't get the H. So you can also think of it as the one richest in hydrogen gets another hydrogen, and the one poorest in hydrogen does not get the hydrogen. So the rich get richer is a way of thinking of this. So he said this is the one that's going to dominate as the result, and it is. About 99% of the time you'll make this. You do make some of this other one. It's called a minor product or a side reaction. Right? And it's the bane of organic chemists because they like to make pure molecules, especially when they're going to make things like pharmaceutical drugs, and you don't want this other molecule around, so you have to purify it away from it, and that could be quite difficult. And the more difficult that becomes, the more expensive it is to produce that drug, and thus the more you end up paying for it. Right? So most of the time, about 99% of the time or greater, right, you're going to make the Markovnikov's major product. We're going to follow Markovnikov's rule, right? So this is the major product, where the asymmetrical double bond is to which is added an asymmetrical molecule, and the carbon that has the most hydrogens gets the hydrogen. That's the rule we'll follow. Hey, let's do some examples. So here's a molecule on the left. It has some double bonds, right? To which we're going to add some asymmetrical molecules, right? HCl's, and I have a 2 here because I have 2 double bonds. I'm going to add HCl to each one. In every case, when we do this Markovnikov addition, right, we're not taking anything away. We're just adding. The double bonds will become single bonds, and one of these will get the H, and one of them will get the other molecule, in this case, chlorine. Okay, so looking at the molecule here, let's do the double bond on the left first. This carbon at the top has how many hydrogens bound to it right now?
1. 0.
0, exactly. 0. So carbon can only make 4 bonds. So this is showing 1 bond here, 1 bond here. This is not a hydrogen, this is a methyl group. And then it's making 2 bonds to the carbon below it. That's a total of 4 bonds. So there are no hydrogens left on this carbon. Okay? How about the one below? This carbon has how many hydrogens?
1.
1, exactly. So it has 1 bond here. It's making 2 bonds to the carbon above it. And there is room for 1 hydrogen here. It's just not drawn. We tend to not draw H's on carbon. Okay? I mean, I could draw it if you want to, but I don't want to confuse you and make you think it's a methyl group. Okay, so this one has 1 H, this one has none. Which of these two is going to get the hydrogen?
The top one?
The top one's going to get the hydrogen. Why? What's our rule?
The bottom one.
The bottom one will get the hydrogen. Why?
Because it's missing hydrogen?
Because it has the most already, right? So we're comparing 0 to 1. 1 is greater than 0. So this one has the most hydrogens of these two, so it's going to get the H, which means the chlorine goes where?
Top.
On
To the
this
methyl?
carbon. It does not go here. I'm not doing alchemy. I'm not going to write chlorine right here, because that would turn this methyl group into a chlorine, and that's not going to happen. That's alchemy. Right? So I'm going to add a chlorine to this one. I'm going to add the H down here, which I don't have to draw. Right? But I drew it for you anyway. So what's going to happen is I'm going to add a chlorine here to this one. I draw a bond, a new one. This double bond goes away. You notice it's single now. This double bond goes away, and I'm going to put a chlorine here. The methyl group is still there. Right? And that's why I picked this example, because I often see students just writing chlorine out here, and they're doing alchemy. Right? So instead, put a chlorine on this one, and put a hydrogen on this one. Yes, there is another hydrogen here as well, the one that was there originally. I'm just not drawing it. I'm specifically drawing this one to show you where they went. But if you were to finish drawing this thing and not include these two red H's, that would be perfectly fine too. The double bond on the right, we go through the same procedure, and we end up with a chlorine on this end for the same reasons, and a hydrogen here for the same reasons. Right? And then we have to name this, of course. The longest chain is still the ring. Right? So it's a 5-carbon ring, so that would be called not a cyclopentadiene anymore. There are no double bonds, just a cyclopentane. And on the cyclopentane, there are still 2 methyl groups, right? And then now are 2 chlorines. So I would name it as 1,3-dichloro and 1,3-dimethyl. But some of you are probably looking, wait a minute, these methyl groups were on 1 and 4. How are they suddenly on 1 and 3 now? They didn't move. But my priorities changed. Here, the double bonds were the priority. So wherever I chose as number 1, I had to go through that one to get to number 2. Or if I started here, number 2, then I must go through the other double bond. So this is 1, 2, 3, 4, or 1, 2, 3, 4. Same thing. I couldn't go 1, 2, 3 because I have to go through the double bond. That's 1, 2. Right? Over here, no more double bonds. So now I'm free to go either direction in the ring. So I'm going to go 1, 2, 3, 4, 5. So priorities change, which changes the name. Remember, double bonds have a higher priority than everything else at this point on your list. So this has no double bonds, so no priority recommendation, so I could go either way, and I'm going to choose the lowest numbers now.
I have a question.
Okay, go ahead.
Why did the double bonds go away again?
So carbon can only make 4 bonds, and what you're doing is each of these carbons, right, instead of bonding to each other twice, only bonds to each other once. Like they have, imagine they're holding on to each other with both hands, right? You reach out with both hands to a mirror copy of yourself, and you're holding on to yourself with both hands. And then you let go with one of those hands. You still have a single bond there, but now each of you has a free hand. And now you're making bonds to 2 new things.
Okay.
Right?
Thank you.
So if you can see that 2 people holding hands with both hands, and if you let go with one of them, you're still connected by one of your arms, and the other can make a new bond to something else. And that's what we're doing. That's why it's called addition, adding new bonds.
So do you only use Markovnikov's rule in addition reactions with alkenes?
Yes, the alkynes don't really matter that much because they're not different at this point, right? They're linear. Doesn't matter which end you put it on. But we'll look at mostly alkenes, and it has to be, if you go back to the previous slide, you'll see it has to be an asymmetrical alkene and an asymmetrical adding molecule. Okay, so that's the ones we'll do. An asymmetrical double bond and an asymmetrical addition. Right? That's the only time you'll worry about it. Okay? Let's go through another one. You guys answer this one for me. So here's another molecule with some double bonds in it. Happens to have 2 again. It could be 1, but I'm doing one with 2. And I want you to figure out where the molecules go. So let's first name this thing to practice. What is the name of this molecule? So longest carbon chain that includes all the double bonds if possible, and it is possible.
1,3-butadiene.
Exactly. Right, so it's butane, if you want to start building the name. So we say butane, it's 4. But there's a double bond, so it's butene. But there's 2 double bonds, so I have to put a di in front of the ene. There aren't 2 butanes there. Don't call it dibutane. Right? It's a butadiene. We throw in the A to make it pronounceable in English. Right? So it's butene. We throw the di in there, but now I have 2 consonants next to each other, and in English we don't like that too much. Right? So we throw in a vowel to make it pronounceable. So instead of butadiene, it's butadiene. And then I have to tell you where they are. They're on 1 and 3. Here they are. Do I need the 1 and 3? Yes, because they could have been on 1 and 2. They could have been back to back, right? Which is entirely possible in a straight chain, not so much in a ring, but it is possible here. Okay? To that, I'm going to add some HI, right? And I'm going to add 2 because there are 2 double bonds, and I have to decide which side gets the H and which side gets the I. So on the left here, let's do that one first. How many hydrogens on carbon number 1?
One. No, two.
2. There are 2 hydrogens here, right? Because carbon always makes 4 bonds. We've got these 2, and the 2H is not shown. Right? How many hydrogens on carbon number 2?
One.
1, right? Because it's got 3 bonds shown, there must be 1 H. Which of those 2 has the most hydrogens of those?
The one to the left.
The one on
first
the left. So it gets
It's the hydrogen.
It gets the red hydrogen. That leaves the blue iodine to go on carbon number 2. Okay, and we'll repeat that procedure on the right, and you'll see you get the same type of answer. The hydrogen goes on number 4 down here, and the iodine on number 3, and we end up with this molecule. Okay, what's its name? Did the number of carbons change?
No.
No. So don't count this as 1, 2, 3, 4, 5 carbons, or 1, 2, 3, 4, 5, 6. Still 4. 1, 2, 3, 4. But now it's just plain old butane. No double bonds at all. On the butane is what? We don't name hydrogens. They're just shown here to show you where they went. You can erase the hydrogens as long as you erase this line along with it. So what is the name of this?
One, 3 iodine butane,
So
or diiodine.
is it on 1? This is carbon 1.
I'm sorry, 2, 3 diiodine butane.
Okay, so you're almost right. We're not going to call it diiodine. Imagine it being 2 chlorines.
Diodal?
Right. So if it were 2 chlorines, you wouldn't say 2 chlorines. You say 2 or dichloro. So instead, we're going to. Somebody has their microphone open. So instead of saying chloro, right, or chlorine, we say chloro. So instead of iodine, we say iodo. We ended in O, like fluoro, chloro, and bromo. So it's diiodo. Yes, there are 2 I's in a row. There are di and then iodo, like chloro, and then butane. Okay, so this analysis where you look at each side, count the number of hydrogens currently bound, right? Make sure you get that right. Whichever one has the most, right, gets the H. Whichever one didn't have the most gets the other atom, in this case I. Okay? Let's do one more example. This one only has 1 double bond, right? So let's name it. It's got 1, 2, 3, 4, 5 carbons with a double bond in it, and it's at position 2. If I tried from this end, it would be at 1, 2, 3, so we're going to stick with 2. So it's 2-pentene. It happens to be trans. Right? Cis would work just as well for this because when we're done, there won't be a double bond. Okay? We're going to add HI to this. Only one of them because there's only 1 double bond. And you tell me which side gets which. So this carbon, the left-hand side of the double bond, has how many hydrogens?
One.
1. How about the next carbon, number 3?
One.
Also 1. So who has the most?
Yeah, the same.
We have a tie, right? They're the same. So how do I know where to put the H? This is an asymmetrical double bond. It's not the same on each side at all. So his rules kind of doesn't apply, right? So we do both. And we actually find out when you do this type of chemistry, you'll get a mixture of both answers in a 50-50 ratio, not a 99-to-1 ratio like all the others. So because there's no preference, there's 1 H on each, we do in fact do both of them. Sometimes the H will go here, sometimes it'll go here. Right? So we get both of those answers in a 50-50 ratio when you do this chemistry. Of course, these 2 things need unique names. So what are the names of these 2 answers over here?
Two iodopentane and 3 iodopentane.
Okay, so 2-iodopentane, that's this one, right? So 1, 2, 3, 4, 5 with an iodine on 2, and 1, 2, 3, 4, 5 with it on 3. That's exactly right. Right, and there's no longer any cis or trans because, like in all these cases, the double bonds are gone. They're single bonds now. Okay?
So if this was on a test, for it to be considered correct, we would have to put both answers?
You'd write both answers and tell me that the product would be in an equal ratio or 50-50 ratio or same proportion or however you want to say that. But you get both. If you go back to this one up here, where you got this 2,3 let me do a better example. Go back to the one with this picture. right? You tell me it would make 2-chloropropane 99% of the time, or you can essentially say this is the answer. I'm not looking for this unless I ask you for the minor product, right? Minor product means it doesn't make it very often, and it's where you don't follow his rule. Okay, so this is called the major product, 99% of the time, roughly. And sometimes, very rarely, it'll make the minor product where you do exactly the opposite of his rule. But in the case we just did, where we have this no preference for either side, the major and the minor product are in equal proportion, so they're not really major and minor anymore, they're equal. Okay, so yes, you'd have to write both, because both are made in the same amount.
Is the point of this trying to break up the bond?
Is the point of it trying to break up a bond? What do you mean by that?
Like, none of them are having that double bond at the end.
Right, so none of them are. When I start, I have a double bond, and I'm making the double into a single, where each carbon now has a room for an additional bond, and each is getting 1/2 of the other molecule, either the H or the I. So these two carbons, right, one's getting the H, one's getting the I. And in this case, there's no preference, so we make both possibilities. See, H here, I here, or H here, I there.
Is that why it's a 50-50 ratio?
The reason it's 50-50 is because there was no preference, right? They each had one hydrogen to start with, so there was no, this one has more hydrogens, the rich get richer, because they each had one, right? If they don't each have one, like with the previous examples we've been doing, then there is a preference, and we only make one major product.
Thank you.
All right, so this next reaction I want to talk about is something you've probably done in lab at this point. Maybe, maybe not, depending on which week you're going to lab. But we're making a polymer. In all these cases so far, we've taken one molecule with one or more double bonds and added some stuff across that double bond. Very simple. But I can take a bunch of these double bonded molecules and put them together into many, many, many copies of themselves. And that's called a polymer, a polymerization. Right? So if I start with a bunch of ethenes, right, and in every case we've been doing, you can use that little hand-holding analogy again. These two carbons are holding onto each other with both hands. Right? You can imagine them facing each other and reaching out with two hands and grabbing each other hand in hand twice. And in every case so far, we've broken this double bond. Each carbon lets go with one hand, all right, and reaches out and grabs two more things. Right? So one thing on this side, one thing on that side. What we're doing in the polymerization reaction is there's no other thing added here. They let go with one hand again, and this carbon reaches out to the neighboring molecule's carbon, as does the neighboring molecule, and we make a new bond between these two, right? Which forces this one to let go with its other hand and reach out across and grab this one, which forces this one to let go. And you notice we see a chain reaction. So we're going to get rid of all these double bonds, and between each of these carbons, we'll make a new single bond. So it looks like this, right? And I don't want to draw it straight across like I have been doing here because it looks really confusing if I just end up with one long straight line. So we end up starting to angle these so you can see the difference, right? And so this carbon here might represent this first one here, right? There are two hydrogens on it. I'm only drawing one of them here, but it does have another hydrogen down below, right? Each of these is a CH2 now. This carbon would be this one, right? The next carbon on the first carbon of the next molecule, the next one in the chain, would be the next carbon over. This is the new bond, right? So this C and C here represent the first ethene, right? This one. And this C and C represent the next ethene's carbons, and this is the new bond between them, right? It's a single bond. Again, here's a new bond between the second and third ethenes. Here's the third ethene. This repeats over and over and over. We do thousands of these put together, and that's called a polymer. And this is how we make something called polyethylene, right? If I weren't using ethylene, if I was using propylene, which we'll see in a minute, which has 3 carbons, it'd be called polypropylene. And if I keep changing what these H's are, I get different polymers over here, right? So that's how we make all these plastics. A very brief way to write this, since we see this ethenes repeating over and over and over and over, I draw it like this. This is my ethene inside, where the double bond has been reduced to a single bond, and each carbon is now reaching out to grab the neighboring carbons of the next molecule. So these parentheses indicate where the bond's going to off the screen here and wraps around and makes the bond to the next molecule. There's a lot of these molecules. N represents a large number of them, right? But this is the repeating unit, right? So this carbon is bonded to here with a single instead of a double. These two are the same carbons. And this carbon reaches out to the neighboring molecule, which is represented by going across this bond to the next one. Here it is again. And they look identical to each other. It repeats over and over and over. So if you haven't done this yet in lab, this is exactly what you're going to do. Okay? But we're not going to do it with ethene. We're going to change these H's to something else. What if the H's...
I have a question.
Yeah, go ahead.
When you were looking at the line angle drawing, how do you know, like if you were given just that, how do you know that it's ethene and not methyl groups?
How do I know these are not methyl groups?
Yeah.
There's an H at the end.
Oh, wait, I just realized I answered my own question because they're not carbons.
Right.
Okay, never mind. Thank you.
I have a related question.
Okay.
So if you were just given that chain, how would you know that it was polyethylene as opposed to like decane?
Well, in fact, if you put 5 of these things together, and only 5, it would make decane. That's exactly right. But we're not putting 5, we're putting maybe 5,000 of them together. So you could call it the 5,000-ane, right, if that's what you want to name it, which would be correct. But we kind of list what it was made from when we name these things, like what was it made from? Right? So this is an ethene, we generally throw the Y in there, but polyethylene, right, is what it was made from. Just tells me, the nomenclature for these in the industry is to tell me it's a polymer of something. That's how we kind of name it. It's not the proper IUPAC name, and I'm not going to ask you that, but I'm just showing you where these names come from. Okay. Let's do one more example. Instead of putting hydrogen here, I'm going to put an X, and it'll clear up a lot of your questions that you're having about how to name it. Right, so I'll put an X here instead. If I polymerize these together, can you see that every other carbon in the chain will have an X on it? Because I'm connecting these. So every other carbon in the chain will end up with an X on it. So it looks something like that. Right? So this carbon has an X. This carbon has an X. There's something wrong with this picture. Can you point out what's wrong with it? Right? I put mistakes in here on purpose so you can find them. So there's something wrong with this picture.
Should there be an X at the bottom between the spaces?
You want to put an X at the bottom. Where should there be an X? Somewhere.
The second hydrogen?
This one?
Yes.
So if you put an X here, then that would mean that these two neighboring carbons, right, both have X's, and that's not possible, right? We have every other carbon with an X. So the X should not be here.
The top H,
this should also be an X, I agree. All right, so here's the change. Make that in your slides. This should be an X, and that's the mistake I wanted you to catch. Right, so every other carbon, which is every up point in this zigzag line, should have an X on it. So this should be an X as well.
Okay.
Right? Another way to represent that would be like this, which is exactly what we said. Every other carbon has an X. So if I go around to the next molecule, right, no X with an X. No X with an X. And it repeats over and over. Right? So we're going to follow that same pattern where I replace this X with various things, right? And here's what I can replace the X with. If the X is just an H, we did that one as our first example, it's just polyethylene. Right? If I replace the X with a whole methyl group, right, this carbon is not going to be in the chain. It's sticking off as a methyl in my original molecule, and it's going to be sticking off as a methyl all the way down the chain. So if you go back and look, instead of X here, we put a methyl group on every other carbon. It's a lot of methyl groups, right? It would look like this, and that's called polypropylene. And a lot of your plastics are made from that. If I replace the X with, say, a chlorine, right, it's now called polyvinyl chloride. Right, this is the typical PVC, so polyvinyl chloride it stands for, or it stands for polyvinyl chloride. This is what you see in the typical water pipes that you use in homes and buildings, right? The white plastic-looking pipes. It's called polyvinyl chloride because this is what it's made from, right? It's very, very good for transporting water without leaching any chlorides out, right? If I change all 4 of those things to F, right? So there are no more hydrogens, they're all fluorines. Then I make something called tetrafluoroethylene because there are 4 fluorines on ethylene, and it got really difficult to say tetrafluoroethylene all the time, so they shortened it to just Teflon. right? Tetrafluoroethylene is where they got the name here by shortening it and some liberal changes in the lettering, and you get something called Teflon. And because these fluorines are there, this really long polymer with all these fluorines, it doesn't stick to very many things. The fluorine is very happy attached to the carbon and doesn't interact with many other things. So it's essentially a non-stick surface, right? So don't scratch it though, because if you scratch this and remove this polymer coating so you can get to the metal underneath, the metal will stick to things, right? So this coating is generally very, very thin, right? And if you scratch the surface of this, the metal underneath will be exposed and it will rust and it will stick to things. So you got to clean these very gently. It's easy to destroy that Teflon coating, right? But as long as it's coated properly, right, nothing will stick. Of course, it's going to stick to these bolts right here because they're not coated in Teflon, right? If I change one of those H's, leave 3 of them alone, change one to a big benzene ring. We haven't talked about benzenes yet, but we will momentarily. But if I change one to a big 6-membered ring with some double bonds in it, then that'll be on every other carbon, right? This line should go through the parentheses here, right? But it should be on every other carbon, so it's called polystyrene, and they shorten that to styrofoam. So if you make this molecule and you puff it up with a bunch of air, it makes our typical styrofoam cups. Okay, so all these are polymers that you make from this ethylene with various substituents on it. Okay. Here's another example. Here's not quite an ethene this time. It's got 2 double bonds. So what's going to happen is they're going to reach out to the neighboring double bond and they're going to make a polymer. These are called isoprenes, right? It's not a typical IUPAC name, but plants make tons of these things, right? We as humans also make a few of them, but we don't make really, really long polymers of it. We make shortened polymers like in cholesterol and things like beta carotenes in some organisms. But plants tend to make really, really long versions of these. They put many of these together and make these really long polymers, right? And that's what we call the natural rubber, right? It drips out of these trees. They put a little spout in the tree, they cut a slash in the tree, and of course it's not the sap of the tree. They can call it the sap, but it's not that. It's a polymer made by the tree, and it drips into these buckets and they collect it, right? The point of this for the tree is to give these trees some less rigidity. So they're not like pine trees where if you get a wind that blows a pine tree, it doesn't bend very much before it snaps. These can bend quite far before they snap because they have this natural rubberized material in them. So we extract it, right, and use it for our purposes. And I'll tell you a really quick story about this. There was a guy who lived in New York, and this was in the 150 years ago, 160 years ago or so. Lived in New York in the late 1800s. And was collecting these saps, these rubberized things from all over the world, right? Had him brought to his tiny little apartment in New York. He was an inventor, and he was trying to turn them into something useful because it was really cheap to get these from the trees. And he was trying to turn it into something useful. All the chemistry he was doing was never successful. One day in his tiny little New York apartment, this was no different than today. The apartments are about the size of a closet, right? The apartment caught on fire. Right, and so all of his stocks of this material were caught in that huge high heat blaze. He lost everything in the apartment, and many other people did as well. And when he went to collect his belongings, he noticed that this material had been vulcanized, right, under very high heat. Right, it changes its conformation a little bit and turns it into what we call rubber today, right, like hardened rubber like we use in tires. And the guy's name was Goodyear. Right? And that's how he came up with this idea for vulcanizing this rubber. It takes very high heat. And of course, he sold that recipe to other companies, and the companies used his name in the future. That's how we get Goodyear tires. Right? So another example is something you will do in lab. This is the polymer you're going to make. Is we do something called copolymers. Instead of having the same molecule repeating over and over and over, you have 2 different molecules. One that looks different than the other, right? This one has 1 chlorine on it. This one has a pair of chlorines on it. And it's very, very unusual in how it polymerizes, but it always does this. Let's call this molecule A and call this molecule B. In the previous examples, we all had the same molecule A, and it polymerized into A over and over. Here, it'll polymerize in a fashion that repeats A and then B, A and then B, A and then B. So when we polymerize this thing, this molecule reaches out to the neighboring molecule, which then this one reaches out to a copy of the first one again. And this one reaches out to a copy of B again. And it always alternates. It's kind of unusual how it does that. So this carbon will have no chlorines, and then we'll have 1, and then no chlorines, and then 2, and then no chlorines, and then 1, then no chlorines, and then 2, and we repeat over and over. So the repeating unit is quite large, right? But no chlorines, 1, no chlorines, 2, because this came from the first and second monomers of my copolymer. And if you make lots of these in a row, we make something called saran wrap. Right? So this is the molecular structure of saran wrap. And the reason it was so useful is because with all these chlorines in this alternating fashion, it doesn't stick very well to food, but it sticks very well to itself, right? Which makes a great wrap, right? You can wrap it around sorts of things. It doesn't stick to food very well, but it sticks to other things like other plastics or wood or glass or something like that, but it doesn't stick to food very well. Some foods, yes, but most foods, no. It'll stick to powdered sugar very well, so don't wrap stuff like that. But this is how you make saran wrap. And lots of other polymers like this were made beginning in the 20th century, in the 50s and 60s, and we've made many, many more since then. Of course, we've made far too many, and now they're killing lots of things in the oceans. Right? The next topic I want to do is what we call aromatic hydrocarbons. So in this case, we start out, let me build the molecule for you. So at the top, we make a hexane, a 6-carbon chain, into a ring. This is not unusual. You've seen this before. We take 6 carbons and we make them into a ring. You know it's not going to be flat like this, right? You've probably played with your model kits at this point. We talked about it before, that it adopts the chair or boat conformation where these angles try to reach 109.5 degrees and you get that bending out of the plane. But I want to take that cyclohexane and introduce a double bond. Right, so now it has a double bond in it. It's cyclohexene. Each of these carbons has lost a hydrogen. Right, they have 2 each. They each lose 1 to form a double bond. Well, this double bond restricts the geometry of this ring. These atoms here, these carbons, are not going to be tetrahedral anymore. Right, they're going to be trigonal planar because they still have a hydrogen here. So 3 Vesper groups. And so all these atoms are going to be planar. That really restricts the geometry of this thing. It's almost a flat plane now. Okay? Then I introduce yet another double bond. These 2 carbons each lose a hydrogen. Right? And then I introduce a third double bond. So now all the hydrogens, or all the carbons have lost a hydrogen, and now there are 3 double bonds in this thing. Right? And it is perfectly flat. Right? There's no way it can be out of the plane anymore. Every carbon is trigonal planar geometry. Every carbon is 120 degrees. It's perfectly flat. So this would be called cyclohexane. This is called cyclohexene because there is a double bond in it. I don't put a 1 here because I know where it is. It's on number 1 by default. Right? Here I put 2 double bonds in the ring. They could have been opposite one another, so it could have been 1, 4. They can't be side by side because then you can't make a ring. So I need the 1, 3 because it could have been 1 and 4. And then I put the third double bond in, and it's on 1, 3, and 5 now. We don't use this name. We don't use cyclohexatriene. We don't use 1, 3, 5 cyclohexatriene. We simply call it benzene, right? Because it's so incredibly stable, right? So this molecule with its 3 double bonds is a beacon of stability, right? We call it benzene because we see it all the time. And these 3 double bonds could be drawn the way you see it, or they could be drawn on these carbons, right? The other 3 that are singles could have been doubles, and these be singles. Right? That gives benzene its stability. It's another way of drawing it. The double bonds move around. So they're not really a double bond, double, single, double, single. They don't really alternate. It's more like every bond between carbons is a 1.5 bond because this alternating pattern. Right? It alternates back and forth all the time. That makes it incredibly stable. So instead of drawing the double bonds like this, which you can do, you can represent it by this figure. You can draw your hexagon and just put a circle in the middle of it. The size of the circle is irrelevant, but put a circle in the middle of it. That indicates that every other one of these is a double bond, much like this figure here. But we don't know which ones they are. It could be these 3, or it could be these 3, right? Because it's delocalized, right? And the formula for it would be 6 carbons and only 6 hydrogens because there's only 1 H left on every one of these carbons because every one is involved in a double bond. Okay. Let's see some properties of these, what we call aromatic hydrocarbons, right? The name aromatic originally came from the fact that these had a smell, right? When you made a lot of these benzene and ring structures, they had smells, and you'll see some of these in lab when you get there. But it adopted a more chemical term later to mean this ring has a delocalized pi system. Remember, if you make a first bond, it's called a sigma bond. Any additional one, this has a sigma and 1 pi. If I were to make a triple bond, it has 2 pi bonds. So what's happening in here is I have 3 double bonds. That means there are 3 pi bonds, and they're all overlapping in the structure. So they're kind of delocalized, which makes it very, very stable. Okay? So let's talk about some of our benzenes. If it's just plain old 6 carbons in a ring with 3 double bonds, we call it benzene. Right? If you have something on the benzene is the parent chain, that's its name, right? And we call the thing on it. Like if it's a fluorine, we call it fluorobenzene. If it's a chlorine, it's chlorobenzene. If it's an ethyl, it would be ethylbenzene, because benzene is the parent chain. So if X were just 2 carbons, right, like that, it would be an ethylbenzene. Or longer things, like isopropyl groups would be isopropylbenzene. If X were simply 1 carbon, a methyl, it's methylbenzene, but we don't call it methylbenzene. Benzenes always get their special names. We call it toluene. There's only one L in toluene. There's no L here, right? It's just toluene, not toluene. Don't say that. And if we put a vinyl group on it, do you remember what a vinyl looks like? We talked about it at the beginning of the lecture. It's 2 carbons long, like an ethyl, but there's a double bond at the end of it, right? That's a vinyl benzene, and that's called styrene, right? And that was the thing that made styrofoam. That's where we get the name, right? But sometimes the benzene itself is not the main chain, right? So if the main chain is something like this, right, which has a double bond in it here, this is priority over a benzene ring. I know this has double bonds in it, but this has priority. We name this as a big substituent. Okay, so you turn to your list somewhere, wherever you're making your priority list, right? And at the bottom of your priority list, you should have written hydrogen. And the next thing up, I think I had you write everything else. Above that was triple bond, and above that was double bond. Well, a benzene ring goes in the category of everybody else, right? It goes in that list of everybody else or everything else. It's no higher priority than anything else like a chlorine or a fluorine or something like that, right? So it goes down there with everybody else. So in this case, even though it has double bonds in it, I know, but in this case, the isolated double bond has priority, right? This thing, even though it's longer and bigger, yes, but it's just a substituent. Treat it as if it were a big chlorine or something, right? So this thing is 1, 2, 3, 4 carbons long, right? And the double bond gets priority, so this ends number 1, right? This does not get priority, so this is number 1. So 1, 2, 3, 4. So it's a butene, right, with a double bond on number 1. There it is. And on number 3, 1, 2, 3, I have a benzene ring. A benzene ring as a substituent is called phenyl. Right, so it's not called benzyl. We save that for something else later we'll talk about. But a benzene ring as a substituent is called phenyl. Right? It's not phenyl, it's phenyl. And it's hard to say if you're from the south. Right? But phenyl 1-benzene, or phenyl 1-butene. And it's on number 3 because it could have been elsewhere. Okay, so these are more vocabulary words I want you to learn. Right? So you got to know what a benzene looks like if it's the parent chain. You got to know what methylbenzene is called toluene, and a vinyl benzene is called styrene. When the benzene ring is not the main chain, when it's a substituent, it gets a substituent name, an adjective name called phenyl.
Is that a methyl group off the ring?
Here?
Yeah, because I mean, like I see the main chain, but then I see the ring, but it looks like a methyl group and then a benzene ring.
Okay, so you're counting things twice. So the main chain is 1, 2, 3, 4 carbons, right?
Okay.
There is no carbon here. This is just a bond.
Okay.
Right? Remember, lines are not atoms. Lines are just bonds. Just like there's no carbon here, there's one at the end. There's no
Gotcha.
carbon. So it's 4 carbons in a row, and this is attached at number 3. This line just represents the attachment, the bond.
Okay.
If there was another carbon, it would come down like this, and then we'd be over here to the benzene ring.
Okay.
And in fact, that's what we would call benzyl, right? But we'll get to that later.
Okay.
Okay.
Okay, so I have a question. Why can the benzene be the parent chain since it has more?
Because the benzene is so exceedingly stable as a group that it's not going to react. And so we tend to put things that don't react as well lower in the priority list. That's just the trend. And that's why triple bonds were below double bonds in your priority list, because double bonds are far more reactive.
Oh, okay.
So this benzene ring, even though it has double bonds in it, they're not very reactive. right? They don't like to do things that isolated double bonds like to do, like addition reactions, right? And we'll see that in just a second. All those ones we talked about. So we tend to just ignore the fact that it has the double bonds and treat it as one big entity, like it's a really big looking chlorine, right? It's called a phenyl group, but we just drop it in the class of everybody else. So that's just a general trend in our priority list. You're going to see that things that are more reactive, right, tend to go higher in the priority list. And that's why double bonds were above triple bonds, and that's why benzene rings are tossed in the everybody else category. Right? The exception was when it's the only game in town, like this chlorobenzene. All the carbons are in the ring, right? So it's clearly the main chain. Okay. So when I have two things on a ring, two things on a benzene ring, exactly two, no more, no fewer, but exactly two, they can be arranged in multiple ways. So you see 4 ways down below, and one of these is not possible. And I hope you can figure out which one it is. All right. So of these 4 that are listed below, where the chlorines are either on the same carbon, so 1 and 1, on, here's a picture of that, right? Chlorines are on adjacent carbons, 1 and 2, or there's a carbon between bridging them, so this would be 1 and 3. I don't go the other way, I go shorter, 1 and 3, or on opposite sides, 1 and 4. 3 of these are legitimate molecules. 1 cannot happen. Which one is it?
The first one.
Why not?
Because it has more than 4 bonds.
Right, this carbon in this drawing has 5 bonds, which is not possible. Right, so this will not happen. We can't do that. So these are the only 3 arrangements of 2 things on a benzene. Right, so the abbreviations for these, we use the Latin prefixes for these. If it's on the same carbon, we call it ipso, because ips means same, right, or self. Right, so ipso. If they're adjacent to one another, they're orthogonal to one another, we call it ortho. We can abbreviate it with a little italic O. If they're as far from each other as possible, right, on opposite sides here, that's the 1,4, we call it para. Para means opposite, right? So ortho next to, para opposite. We have one that's kind of in between those two, right? So this is 1,2 and this is 1,4. So in between ortho and para is the one where they're on 1 and 3, so it's called meta, which means between, right? So meta is between the ortho and para, literally, right? It's because it's 1,3 instead of 1,2 or 1,4. So we can't have ipso, right? I want you to know the prefix because I want you to learn these terms, but we can't have that with benzene rings. But we'll only use ortho, meta, and para with benzene rings. We won't use them with the non-double bond stuff. So I want you to know the term ipso only for the fact that it can't occur in a benzene ring. Right? And then the ortho, meta, and para we'll only use with benzene rings in the 1,2, 1,3, or 1,4 conformations. So these are written as either 1,2 dichlorobenzene or simply call it ortho dichlorobenzene because the ortho represents a 1,2 arrangement, right? Or meta or para for 1,3 and 1,4 respectively. Okay. All right, the last thing I want to do is reactions of these benzenes. Right, so they also react, but I want you to write this down in bold print, highlight it, whatever. These aromatic hydrocarbons, like benzene, do not do addition reactions. I know we did a lot of addition things before, where we turned it into a single bond and added something to each side, but these aromatic benzene rings do not do addition. They will always do substitution. Okay? That's a major fact you have to know. So if I add something to this benzene, here's a benzene, I'm adding an asymmetrical thing again, remember this, 2 parts. We have an ethane part and a chlorine part. We're not going to take this double bond and break it and put ethane on one side and chlorine on the other. That is not how it works. Okay? We will never do additions to these benzene rings. We'll always do substitutions, which means I'm taking something away, usually a hydrogen, and replacing it with something else. So basically, think of them as exchanging partners. So there's a benzene, there's an H on this benzene right here. It's not drawn, but it's there. Right? There's one on every carbon, but this one right here. And in this chloroethane, there's a chlorine attached to this carbon, right? And what these 2 carbons are going to do is switch, right? So this carbon containing its chlorine is going to give the chlorine to the hydrogen, and the carbon is going to make a bond to this carbon. So you notice this 2-carbon group is now attached here. So 1, 2 carbons. This CH2 that had the chlorine on it is this one right here. This CH3 is the one on the end. This red line is not a carbon, it's a bond. Right? So this carbon down here was the one that was originally there. The hydrogen that was here is no longer there. It's attached to the chlorine, and that leaves as HCl. Right? So it's a substitution. You see, I've replaced the H with this carbon chain. And this is how we make carbon-carbon bonds in chemistry. Right? We use these replacements to put things on here. Right? This is called alkylation because I'm adding an alkane. Right? A carbon chain, an alkane, is being added to the benzene. And in fact, a 2-carbon chain, so it's an ethyl benzene at this point. At the bottom here is halogenation, but remember this is again a substitution, not addition. So halogenation, before we termed it as addition. In this case, it's a substitution because these things don't do addition. So don't think I'm replacing this with a single bond and putting a bromine on each. They don't do that. I'm replacing this H with one of these bromines, and the H leaves with the other bromine. You see how they kind of switch partners. So that's what these guys do. All these aromatic rings will always do substitution, not addition. Okay? And then the last slide I want to briefly mention to you, you don't have to memorize this, I'm just giving you some context, kind of like the vision thing we did earlier. If you take 2 benzene rings and don't bond them together, but fuse them, right? That's a different thing. They're not bonded to one another by a single line, they're sharing a side, right? So it's 2 benzene rings that are fused together. Right? This isn't 12 carbons. It's not 2 benzene rings bonded together. That would be 12 total carbons. This only has 10 carbons because they're sharing a pair of carbons. Right? There are no H's here on these carbons. This is called naphthalene. Right? It's what you find in mothballs. Right? It's the chemical in mothballs. Right? If you take 3 of these and put them together, you get what's called anthracene. You don't have to memorize these names. Right? This is just slightly longer, and you can keep making these longer and longer. But if you take 3 of them and put them together slightly differently, instead of 3 in a row, let's take these last pair and they share this side instead. Right? So one here sharing this side, and the next one would share this side with it. That's called phenanthrene up here. And it has a very, very distinct part of it. Right? All these rings are perfectly flat, they're planar, but it forms this little cavity here. Right? And this little cavity is found in lots of other combinations, like this one, or this one down here with many benzene rings together. They all have this cavity, right? And this cavity is known to be a carcinogenic feature, right? So these molecules with these cavities that look like this shape tend to have cancer-causing properties or mutagenic properties in certain cells. So that's why these things you have to be careful with when they're found in lots of other products, right? That you don't want to expose yourself to a lot of these things because they have a tendency to cause mutations, right? Whereas naphthalene and anthracene don't have that feature, so they're less carcinogenic. But they will kill insects very well. Right? But these will also do that. Right? So next time we'll talk about alcohols and phenols. We're going to introduce a new element, right? All the things we learned so far, but we're going to introduce a new element, oxygen.